Hello everybody, this is Mika Seppälä. This video discusses properties of integrals and numerical integration. Everything here follows from the definition of integrals right away. This video is a preparation for the fundamental theorem of calculus, which is a cornerstone of this area of mathematics and allows us to compute values of definite integrals easily by evaluating antiderivatives. In this video, I consider properties of integrals starting from the definition and numerical integration. The starting point is the definition of definite integrals. In that definition, one considers first Riemann sums, which are sums of the form summation k from 1 to n, the function f evaluated at some point tk on the kth subinterval times the length of the kth subinterval delta of x. And as one takes a limit as the length of the longest subinterval goes to 0, then at the limit one gets the definite integral of the function f over the interval from a to b. Geometrically, that is related to areas. So if the function f takes positive values, then the area of the domain under the graph of this function contributes positively to the value of this integral. If the function takes negative values, the contribution is negative of that area. So in the case of this function in this picture, the definite integral from a to b f of x dx is the difference of the areas of the two blue domains and the one red domain, corresponding to negative values of f. The first property that follows immediately from this definition is that the integral from a to a of f of x dx is always 0. That is, the integral of any finite function over an interval of length 0 is always 0. And this is immediate because in every Riemann sum approximating the integral from a to a f of x dx, these terms delta of xk, which are lengths of the various subintervals into which the original interval has been divided, all these terms are 0, because the length of the original interval of integration is 0. Therefore, every delta of xk is 0, and this means that in all Riemann sums, all terms are 0, and therefore also the limit of the Riemann sums is 0. The second property says that the integral of a sum is sum of integrals. That is, integral from a to b of f of x plus g of x dx is integral from a to b f of x dx plus integral from a to b g of x dx. This is also immediate because every Riemann sum is of the form k from 1 to n f at tk plus g at tk times delta of xk. All these finite sums can be split into two sums. So all Riemann sums k from 1 to n f of tk plus g of tk times delta of xk can be written as summation k from 1 to n f at tk times delta of xk plus summation as from k from 1 to n g of tk times delta of xk. And then we take a limit of this sum of Riemann sums, and since the limit of a sum is sum of limits, we conclude that this limit of the sum is integral from a to b f of x dx plus integral from a to b g of x dx. Since all Riemann sums are just finite sums, we may rearrange the terms any way we wish, and the sum does not change. The third property of integrals says that integral from a to b a times f of x dx equals a times integral from a to b f of x dx for any number a. That is, a multiplicative constant can be taken outside of integration. This is immediate, since integral from a to b a times f of x dx is limit of the Riemann sums of the type k from 1 to n a times f at tk delta of xk. Now a appears as a factor in all terms of the Riemann sum, therefore it can be taken outside of summation as a common factor. So we conclude that integral from a to b, a times f of x dx is limit of the expressions a times summation k from 1 to n, f at tk delta of xk. But again, by properties of limits, this a can be taken outside of the limit process. So this is a times limit of the sums k from 1 to n, f at tk times delta of xk. But this sum is a sum, Riemann sum, for the integral from a to b of the function f of x dx. Therefore we conclude that this is same as capital case A times integral from a to b f of x dx. That is, a multiplicative constant can be taken outside of integration. The fourth property of integral says that integral from a to b f of x dx is negative of integral from b to a f of x dx. And this follows immediately from the definitions. Namely, on the left-hand side we consider the interval from a to b, and on the right-hand side we consider the interval the other way around, from b to a. So when we form the integral from a to b f of x dx, we consider Riemann sums, summation k from 1 to n, f at tk times delta of xk. And we take limit of these Riemann sums. But these sums are of the form summation k from 1 to n, f at tk times xk minus xk minus 1. But now if we transverse this interval from b to a rather than from a to b, we consider the quantities xk minus 1 minus xk instead of xk minus xk minus 1. So we observe that this is negative of the limit of the Riemann sum summation k from 1 to n, f at tk times xk minus 1 minus xk. And this is negative of integral from b to a f of x dx. Therefore, this fourth property comes immediately from the definition. The fifth property of integrals says that integral from a to b f of x dx equals integral from a to c f of x dx plus integral from c to b f of x dx. If c is between a and b and f takes only positive values, then these integrals correspond to areas, and this property is completely obvious. Integral from a to b f of x dx is the area of the domain under the graph of the function f. It is the blue curve shown in this picture, and over the interval from a to b. That is this integral on the left-hand side. The integral from a to c f of x dx is the area of the blue domain here, and the integral from c to b f of x dx is the area of the red domain. Together, this blue and red domain, they cover the interval from a to b, and therefore the combined area of this blue and red domain is the same as the area of the domain under the graph of the function and over the interval from a to b. This property is valid even if c is not between a and b, and even if function f takes negative values. To summarize, we have observed that integral from a to a f of x dx is always 0. We have also observed that the integral of a sum is sum of integrals, that is, integral from a to b f of x plus g of x dx equals integral from a to b f of x dx plus integral from a to b g of x dx. Then we have observed the property number 3, integral from a to b, a times f of x dx is a times the integral from a to b of the function f. And this is valid for all numbers a. So a multiplicative constant can be taken outside of integration. The fourth property was that integral from a to b f of x dx is a negative of integral from b to a f of x dx. And finally, the fifth property was that integral from a to b f of x dx equals integral from a to c plus integral from c to b of the same function. Integrals are limits of Riemann sums. This gives an easy way to approximate integrals numerically. A general Riemann sum is of the form summation k from 1 to n, f at some point tk on the kth subinterval times the length of the kth subinterval. Now we may use a decomposition in which every subinterval has the same length and in which there are n subintervals. So we would decompose the interval from a to b into subintervals, where the first one would be a, and then a plus b minus a divided by n, and then next one would be from a plus b minus a divided by n to a plus 2 times b minus a divided by n, and so forth. So the general kth subinterval in this case would be the interval from a plus k minus 1 times delta of x to a plus k times delta of x, where delta of x is b minus a divided by n. And then we may let n grow to get a good estimate. We still have to decide how we choose the points tk from the various subintervals. We may use the left rule, in which case the point tk is the left endpoint of this corresponding subinterval. Then tk would be a plus k minus 1 times delta of x. This picture here shows a left rule approximation of the integral of the function whose graph is the red curve shown in the picture. We may use also the right rule, in which case tk is a plus k times delta of x, and this picture illustrates a right rule approximation of this integral. Or we may use the midpoint rule, in which tk equals a plus k minus 1/2 times delta of x. This picture here illustrates the midpoint rule approximation of the integral. To summarize the numerical integration, we observe that we have used a decomposition of the interval of integration from a to b into subintervals of equal length. If there are n such subintervals, then the length of each one is delta of x, which is b minus a divided by n. Once we have decided to use such decomposition of the interval of integration into subintervals, we still have to choose the tag points in some fashion. The tag points, the points tk from each subinterval, may be chosen to be the left endpoint, the right endpoint, or the midpoint of the corresponding subinterval. And that yields left approximations, right approximations, or midpoint approximations, and these pictures illustrate these 3 different approximations. Depending on the behavior of the function, one of these approximations may be better than the other ones, but regardless of that, if we take n large enough, these approximations get as good as necessary. So in this way, one may numerically estimate integrals, and one may get a very good idea of the actual value of a given definite integral just by computing Riemann sums of this type.